particularly which can encompass various aspects of standard model. And it came very close to predicting the Higgs mass also, quite some time back with 170 GeV. It was although ruled out, but later they modified the model, and it was studied in detail how to reconcile non-commutative geometric model Ella, Cones et al. With the observed experimental details. So Fedele is an expert in this area, and I'm very happy that he has accepted my invitation to come here. And it is very nice also to have Professor Epi Balchandran, under whom he carried out the research work in his PhD research work in way back in 80s in Syracuse University. So after that he has continued to work in various aspects of non-commutative geometry, particularly its relationship with say weak rotation and things like that, because as you know that non-commutative geometry is essentially formulated in Euclidean space-time. So Lorentzian manifolds are still a bit of problem. People are working on these aspects as well. So he will talk about how to accommodate all these features in the existing framework of non-commutative geometry. He is expert on this line. So I request Professor Balchandran, being his supervisor, to say a few words about his accomplishment before he can start.
Okay. This will be a very short memory of the times when Fedele was in Syracuse. That was also the, I would say, the golden period of our physics research in Syracuse. Fedele was there, and some of you may know Vincent Rogers. And there was still they talk about Vincent Rogers and Fedele being in Bangalore together and walking down the road.
In 84. In 84.
In 84. Our relationship has continued to be very special. I even know there is a room reserved for me in his house, in his flat. So whenever I go to Napoli, I stay there. He has, of course, done very good work in Syracuse, but subsequently he has expanded his horizons, and now he is he gets invited everywhere to give lectures on this topic. So you can see how much he has established himself.
In fact, you may Corfu or Vietnam coming up, because this is the series of lectures which I've given in Corfu and Vietnam. So sometimes I checked again that we may see here in Corfu, and
I should
here
remember
to change.
who are the people there. I said Fedele, but I see that Kumar is here, Kumar Gupta.
Yeah.
Then I see Amitabh Lahiri, who is sitting there. There are others who are not here, namely Ajit Srivastava, who is not here. So quite a few people.
Sachin Vaidya.
Sachin Vaidya, who is in Bangalore. They were all in the, I would say, the golden period of research in Syracuse. Those times are past, but anyway, when it lasted, it was very good. So
So many BAL students that when we organize a conference in honor, we already did twice. We always the worry of have we forgotten somebody when we make the invitation. Anyways, yes, I will talk about non-commutative geometry and particle physics, but I will start talking more in general on non-commutative geometry. Non-commutative geometry is something which cuts across mathematics and physics, and there are many flavors of it. In fact, next week there is a conference, and you will see various flavors, including my talk that will be not on this next week. I will wear a different hat. The reasons, so I will, since there is a whole conference next week, I will not dwell too much on the reasons for the need of a non-commutative geometry. They will come out, I prefer them to come out in the explanations. I just remind you that the original non-commutative geometry is the quantum phase space, namely, and we'll see how things will come out, but I want to give just one motivation for the need to expand our visions of geometry, and this is a version of the Heisenberg microscope. It is due to Bronstein, and Bronstein was a Soviet physicist, and he disappeared one day, was taken by Stalin police, and was shot actually the day after he was arrested, although the family was not told. And so this work didn't, well, he wasn't there to push for this work that it was written shortly before, and he did other things, and this unfortunately was published in German, also in Russian and German, so it's been translated later on. And
Here's the first person to say, compute three-level scattering amplitudes in point
Yes.
gravity.
Yes. No, he did some important work. Actually, he was quite young, but he disappeared. And also, since he had disappeared, probably other physicists that knew about his work were sort of reluctant to quote him. So the memory has been sort of lost, but was found again. Actually, Andrianov told me about this work, and then it had been now it's translated and it was published somewhere in a journal in English. Let me give you a very quick and very heuristic way. Now, if I want to explain the Heisenberg principle, the usual one of quantum mechanics, I can use the so-called Heisenberg microscope. So if I'm trying to see where something is, I will have to shine light on it, or some other form of radiation. Of course, much better light than a beam of W particles with mass. But so I illuminate it, and then I see where it is. And to see means that I do scattering, and then I collect the reflected beam of light with some microscope. Now, if I want to be very precise, I have to have a very short wavelength light. But then, because of the presence of h bar and c, so of special relativity, you know that the energy of the photon, which is quantized, is proportional to h bar and the frequency, so inverse to the wavelength. So a short wavelength means a lot of energy. A lot of energy means also a lot of momentum. So if I try to look at something very small with something with a lot of momentum, the scattered particle will have an uncertainty, which is due to the very energetic photon. So you cannot really localize something without giving it a big kick. And so if you give it a big kick, it means that you don't know the momentum immediately afterwards, because there is unavoidably a momentum transfer. And so this is, of course, this is a very heuristic way. In fact, if you do it with all the calculations, you will find the uncertainty limit is h, not h bar, and not h bar by 2. So there is a factor, there is a factor of 4 pi, which is a big one, but still is a heuristic way. Now, we can say, well, I don't care about momentum. I only want to know where the particle is at some instant. Then what happens afterwards, I don't care. But now, if I insert G, and so I have to take into account general relativity, and I remain at the heuristic level, I have restrictions. The problem is that if I concentrate too much energy in a small volume now, I create a horizon. So I cannot see inside of the black hole. So even if I don't care about anything, automatically sending a lot of energy in a small volume, so if I want to know where the particle is, I cannot go below the Schwarzschild radius of a certain particle, and so I have a limitation. Now, this is highly unsatisfactory as an explanation, and when we do quantum mechanics, of course, we can say this on the second or third day of our quantum mechanics class, but then we derive the Heisenberg uncertainty principle when we do the theory of operators on a Hilbert space, and then we define delta P, delta Q, we calculate it, and there are a few proofs, and then you find that actually the limit is h bar over 2. So I would have to do the same thing, but I cannot, because I would need quantum gravity. I don't have a theory of quantum gravity on the same level of the theory of quantum mechanics. So I cannot do the proper way of doing this. So, what can I do? Well, clearly, the important bit is the structure of space-time, and I can try to see what are the tools of mathematics that can help me doing this. The tools are likely to be related to the other ones. So it's unlikely that there will be the same kind of non-commutative space, although people have studied the Moyal spaces, which is essentially this. But it's likely that probably the way of describing this will be the same. And so for the first lecture, I will try to describe in general terms the non-commutative geometry, and I will do following Cohn's view. As I say, there are various levels, and for these lectures, I will be using the theories or the ideas that go back to Alain Cohn or even before to Gelfand and Nyberg, and I will see. Now, as for what I say, there is a natural scale for this geometry. You know, physics is mathematics with scales, with dimensionful quantities, and the dimensionful quantities is the Planck length. But then there is, and this is the arguments of my talk, there is an interpretation of the standard model of particle interaction. So the standard model of particles, the one that is studied at LHC, the Higgs, and the phenomenology one, which is can be explained as a very simple non-commutative geometry. So the one uses a tiny corner of the machinery of non-commutative geometry, and in particular, space-time is still classical, so there will not be Planck length, and the non-commutativity is the most trivial non-commutativity, matrices. So the most numbers commute, and when one wants to describe non-commutative at the beginning student, one takes 2 by 2 matrices or matrices anyways. That's the first example of non-commutativity. So I will have a classical space-time, and a non-commutativity will be in a matrix algebra. So we call this an almost commutative geometry, and I will give this with I will describe the standard model as this kind of non-commutative geometry in a way that can be confronted with experiments and hopefully to make correct predictions. As Bishwait was saying, predictions had been made and they were not the right one, but one has to improve on the model. I will discuss this very much in detail as we go along. So the plan is as follows, and not all lectures are of equal lengths, so I may carry some of them to the following session or finish before, and I may cut the material in the end. I have also exercises, so perhaps after 1 hour and a bit, I will pause and I will do some of the exercise which I assigned. Because in Corfu was a school with exercise sessions, was a real school. I wasn't grading them, but there were. But I will ask some questions and then I will give myself the answer. Some of them if you want to take. So today, the first lecture, I will introduce non-commutative geometry from the spectral point of view, and not only to set the stage for further developments in standard model, but I want to indicate a philosophy, because I think that this spectral point of view in physics and mathematics is a very productive philosophy. So really, there will be, I somehow here there is the Bashish, we are doing the same thing in philosophy, although if you listen to my talks and to his talks, perhaps very little is in common. I will talk of the mass of the Higgses, he will talk of categories, but what is at the root is the spectral philosophy. It's really the point of view, which is the point of view of one, probably it's Heisenberg quantum mechanics, no? So everything starts from Heisenberg matrix theory, not to speak badly of Schrödinger, but everything is algebraic. You know, the point of view of Schrödinger is partial differential equations. In fact, even in my classes in quantum mechanics, I always tend to be algebraic. So this will be the first lecture. Then the geometry will be simpler, will be, as I said, an ordinary space-time by finite matrices, but it will apply this to the standard model of particle physics. So the physics becomes more complicated, and the second lecture will introduce the standard model as a non-commutative lecture. In the third lecture, I will confront with the actual standard model. So I will try to give numbers and to see where numbers are coming from. I will not do all the details calculations, but indicate they are, and then one can look at it. And then in the fourth lecture, if I get there, I will discuss the open points, which is basically how to do Lorentzian, how to make this model Lorentzian. So because up to then everything will be Euclidean, and I will discuss a little bit this. Also, this is an open problem, and there are also various solutions, and I will discuss, of course, my own. Because okay, so let's start from commutative to non-commutative geometry. And since I want to discuss physics, I want to also mention the fact that geometry has always been very tight, close, very tight, always tied closely to physics. I was getting commutatively of the words. And since with a bit of nationalistic, I will offer a quote from Galileo from the Dialogo sui massimi sistemi: è forza confessare che il voler trattare le questioni naturali senza geometria è tentare di fare quello che è impossibile ad essere fatto. This is my own translation, and he says that you must confess that to treat matters of nature without physics was starting at the moment. The word physics was not in the vocabulary, it was natural philosophy. Without geometry is to attempt something which is impossible. So, but what is geometry? And to define it, I will take the highest authority nowadays, which is Wikipedia. When in doubt, we look at Wikipedia. And geometry from Geos and Metron, so from Earth and geometry, is the theory of measurement. It's a branch of mathematics which concerns with questions of shape, size, relative positions, and the properties of space. So this is geometry. And physical theories not only use geometry, but they are geometry. So analytic mechanics, rational mechanics, is the symplectic geometry of phase space. So this is really vector fields and everything, or general relativity is basically Riemannian geometry. So the theories are really naturally very tied with tied physics and geometry. But there is a crisis, and the crisis, of course, with quantum mechanics, because what is based on geometry, or even less than geometry, topology, so the basis of geometry, is points. So it's a set made of points, open sets, and then you take points and you connect them, measure, and so everything starts with the point. But if you have quantum mechanics with, as I say, you cannot really localize things. And so the concept of points goes away. And so we need to do something, because the point is not there, and the algebra of functions, which are functions from maps from a point into complex or real numbers, is not there anymore. And so what should we do? Well, instead of having commuting functions of P and Q, we have non-commuting operators. So we are substituting, for example, the coordinate x function or angular momentum, no, they are function of x and p, and we substitute them with operators. So a function of x and p becomes an operator, and but one thing doesn't change. What is the state of a physical system? And this is a map. Sorry, this is a map from an algebra into complex or real numbers. This is an observable, it's a real number. So, for example, I take the function angular momentum. Classically, the particle will be in a point in this space. And then I look at this point, it will have 6 coordinates, and I will have, it gives me a number, x1 p2 minus x2 p1, and this is the angular momentum of the particle. So a state is a point in classical state, in the quantum phase space. This is a pure state. I can also have non-pure states, they are probability distribution. So this is a classical point, which is a map from the algebra of functions of P and Q into, say, a real number if it's an observer. In quantum mechanics, it's the same. It's a map from operators, self-adjoint, into real numbers. If it's a pure state, it will be a particular matrix density, or it can be described by a vector in some Hilbert space. Otherwise, it can be a mixed state, and it will be the same. So it's the unifying idea is that you start with an algebra, commutative, classical, or non-commutative quantum, and then a state is a map into the numbers. So that's the starting point. So let me do first commutative geometry, and even less. I will discuss here of out of topological spaces as commutative algebra. And there are some series of theorems, mostly due to Gelfand, Naimark, and Siegel, which connect the C-star algebra and out of topological spaces. So let me describe slightly detail what those are. A C-star algebra is an associative algebra, so not a Lie algebra. So I multiply things and they are associative. Normed, because there is a norm, over a field, depends on, think of the complex fields and you are okay. Of course, if you do these things as a mathematician, you can go into p-adic or anything, but for us, the complex are enough. With an involution, which I call star, which is a generalization of the complex conjugation, with some properties, and quickly the properties are the triangular inequality, various inequalities, the triangular, and I never remember the names, but you know, there are these inequalities. Then alpha is a complex number, and if I take the norm of the element of the algebra, I can take away the complex number. I multiply this by a complex number and take the modulus of the complex number times the norm of the algebra, and this is important. And if the norm is 0, this implies that the element of the algebra is 0. And now this instead relate to this evolution. The norm of A star or A dagger, for matrices will be the dagger, is equal to the norm of the original element. And this is what makes this a C-star algebra or a star algebra. This is then a non-trivial one. I'll give you examples for which this is not valid. Now, a C-star algebra is complete in the topology given by a norm. So if I have a normed space, immediately I can define a topology between the elements of the algebra, and it has to be complete, otherwise we call it a star algebra, and I have to complete it. In order to make sense, this completion must be unique. And some examples of C-star algebra. The matrix is n by n can also be 1. And in this case, the star is Hermitian conjugation. Matrices with values in the complex number. The algebra of bounded or compact operators on a Hilbert space, again with the Hermitian conjugation. Kumar had a question?
So, is the topology derived using the metric induced by the norm, or is it independent of that?
Yeah, in a metric induced by the norm.
With that.
Yes, so the convergence is given, is a strong convergence. It's when a sequence converges to something, if the norm of an converges to the minus a converges to 0. So that's the...
So it may not be equipped with an inner product.
No. In fact, the counterexample, I give something which looks like a sister algebra, but is not for this. It's a Banach algebra, but there are Banach algebras that is not. It's a Banach space, but it's not an Hilbert space. So there is no. I don't have an inner product. I may have it, but I don't require an inner product. I can define one, but completions and norms will be different. In particular, this is not a norm which is valid if the norm is induced by the inner product. Okay, so think, for example, of the L2. It's an example that I was going to mention later, but this is maybe a good moment. Think of the L2 norm, okay, which is a scalar product. And now this is not satisfied. The norm of the integral of the norm, so this is not satisfied by this. So an L2 space is an Hilbert space with will not give rise to a schizoidal algebra, even if you complete it. Okay. Now, in fact,
the above inequality mod of AB should be less than or equal to mod of A times mod of B. Operator.
Yes. Sorry. Yes, of course. Yes, a B can be 0. Yes. Sorry, it's just a
norm of
just a typo. So I think the typo is that the comma. This comma must be here. So norm of AB must be norm of A times norm of B, comma. Norm of A must be larger than 0. Okay, it's a misplaced comma. This is the typo. And another example which is relevant is the algebra of continuous functions over an Hausdorff space, vanishing on the frontier in a non-compact case with pointwise multiplication. This is a sister algebra, but the norm, so the first involution is a Mittern conjugation, but in the second, that's what I say, this one. And now let me discuss about norms. So take matrices. Now you have this is a norm, okay? Or take functions, and this gives a norm, okay? In particular, this is the norm that you would get if you have a scalar product. And they come and they create a Hilbert space structure, but they are not good norms for a star algebra. They are not the norms that I wanted with this property. Okay? There are proper norms on this space. So the space of matrices and the space of continuous functions over an Hausdorff space have a norm. But these two norms are not the one that would come from an Hilbert space structure. For example, for matrices, you can take the maximum eigenvalue by Dagger A. This is a norm with all the properties. And for functions, and that's why they have to be continuous over a compact space, or if the space is non-compact, I want them to go to 0 on the frontier, otherwise, because I cannot have, they don't have to go to infinity. So if the function is continuous function of x, there will be a supremum of this function, and this is a good norm. Okay? This is relevant. So, if I have a Hausdorff space, any Hausdorff space M, so I can always canonically define a commutative sister algebra, and they are the continuous complex valued functions. And if M is compact, then the algebra will be unital. It will contain the identity. An algebra did not contain the multiplicative identity. It has to have the 0, but in fact, the example is functions over. Think of the line, functions of the real line going to 0 at infinity. This is a good algebra. I can sum elements, I can multiply them, and I will not have any surprise because they are continuous and they go to 0 at infinity. So if I sum them, if I multiply them, they will keep on going up 0 at infinity and they will be continuous. But the identity is not a part of this algebra. Okay, but that's okay.
I have another question.
Yes.
For continuous functions, a sequence of continuous function need not be continuous, right?
In which norm?
The-
That's the point. That's another. With this, you complete with L2. So I take a sequence of functions which goes to the step.
Yes,
It converges in L2,
right.
but not with this norm.
So that's what I'm saying. So the sequence need not be, and the limiting point of the sequence need not be in the space itself.
It is. With this norm, it
If
is.
it converges uniformly, then it is. It depends on which norm you use. So if a sequence of continuous function converges in smooth norm, then the limit is going to be non-uniform.
Yes. Because
that's
the-
the-
because if see that if I should have that you want to have that the norm of Fn minus F must go to 0. Okay? Now it depends what norm I'm using. If I'm using this norm, then I can easily, since it's a non-local norm, the integral can go to 0. But if I use this norm, I should have that the maximum value in which the two functions differ must go to 0. And I cannot do that because of this is the difference in norms is fundamental. It's really the important bit. So, and this is something that people often get confused. An observable is not an L2 vector. An observable must be continuous. And the same is for operators. This is this one means that you cannot have a sequence of bounded which goes to unbounded, which you would have in the weak norm. No? It's 1, 1, 1, 2, then not 0, 1, 2, 3, then not 0. Then the sequence, but the convergence of these to the number operator is in this norm. Well, is in this norm, not in this norm, because in this norm there is no convergence. There will be the distance will always be 1 between the first thing.
Not even in that, not rather weakly. The stress inversion will force you to be.
Yes, it's true. That even this one, but there are lots of norms that you can put, and in fact. But I will stick with this with these ones. They are so now the important element is that the result is true. So what I say is that if I have a compact Hausdorff space, I can always give you canonically a sister algebra, continuous functions with values in the form. Right? And so this is a commutative sister algebra, of course. They are functions. Another important bit is the result, the inverse is also true. So, I come with a commutative sister algebra. So I come and I give you a bunch of element vectors to the infinite. That I give you some vectors and I give you some rules to sum and multiply them. They will always be, no matter what, the set of functions continuous in values in the complex over some out of space. So if I have an out of space, I have a commutative sister algebra. And if I have a commutative sister algebra, I have a Hausdorff space. And you have to use all of the properties of the sister algebra. In fact, there are examples in which you just take away, and we just saw one. You just take away one of the rules, and then you don't get anymore a unique way, or you don't get an outer space, or whatever. So everything has to be there. In fact, this is a result by Geffen and Naimark. It's now sounds trivial because the construction is constructive, but at the time of Geffen and Naimark, you needed Geffen and Naimark to do it. And the proof is constructive. So if I have a sister algebra, I can reconstruct the points and their topology. And to do that, I need the notion of state. So you see immediately the notion of point and the notion of state get connected. So a state for me is a linear functional from the algebra into complex number, which is positive, and is of norm 1, and namely, I can define the norm of this, it's a linear function, so I can define the norm, and it's the sup of all the on all the elements of the algebra with norm smaller than 1 must be 1. So this is the definition of the norm, and this is the requirement of being a state. Then this is actually a consequence. If the algebra is unital, then the state will give you 1. So this is a state. And the space of states is convex, namely a linear combination of two states. Now this is the cosine square of lambda. They are just two numbers whose sum is 1. Is still a state for any value of lambda. So if I take the sum of two states, phi 1 and phi 2, and I take a convex linear combination of this kind, I still have a state. And some states cannot be expressed as this sum. They form the boundary of the set of states, and they're called pure states. Okay, physicist audience knows this concept of pure state from the matrix, density matrices. No? If I have a matrix which is not a pure state, I can always take it as the sum of two other matrices with coefficients which renormalize. But if it's a pure state, in some basis will be a 1 and everything will be 0. And I cannot make it as a sum of two other states. And
so since you don't have an inner product,
mhm.
there is no natural isomorphism between the algebra and its linear function. So
Yes. And
that way, that's okay.
No, I don't need it.
That's not a problem. That's essentially quantum mechanics for the state and Rao, etc. correspond to each other.
Yes, but I only look at density matrices. So a density matrix is a number of this kind: row 1, row 2, and then some of them may be 0. So trivially, this one will be the sum of a matrix of the kind alpha 1, row 1, and then everything 0, plus 0, and then some other coefficient, alpha 2, row 2, and then everything else. Okay? So that's what I need. So I don't need the Hilbert space, I don't need everything. Unless, of course, so it will be a sum of, for example, this sum. Okay, if the matrix, however, is 1, 0, 0, 0 in some basis, then I can never write it as a sum. So this is a characterization of a pure state. Okay? In this case, I have that. In this case, of course, for functions on some Hausdorff space, I will have something different, but I will say something. Now, as first exercises which I gave, you have to find the states and the pure states for the algebra of n by n matrices. See, the concept of states is not, of course, only for commutative commutative C-star algebra, but also for non-commutative. And there are the notion of states, and this is actually a quantum mechanical problem. And for a commutative algebra, the pure states coincide with the one-dimensional irreducible representation, and as well as the set of maximal and prime ideals. So if you know what an ideal is, okay, otherwise it's not crucial, because it's a different characterization of the set of states. So there are different characterization of the set of pure states, which are the points, for C-star algebra, and they coincide in the commutative case, and they don't coincide in the non-commutative case. This is because when somebody talks of non-commutative geometry, what is the generalization of a point is debatable, because there are three concepts which coincide in the non-commutative case, and they don't coincide in the non-commutative one. So according to which generalization you want, you may call things, they're just names. There is no conceptual things. Okay, now you can have I'm telling you that the states are the points and the pure states coincide, so I can reconstruct from algebraic data the set of points, but I have to give you the topology. And this is very simple. So let me take, and the names are suggestive for physicists because I call delta, and this is suggestive for delta function. So let me take a succession of pure states which I call delta xn, and I define the limit of this succession of pure states as this. I want that delta xn of A equals delta x, so x is the limiting state. This has to be true. So for any A from any element of the algebra, the state, which is a number, has to converge to the number given by x. So this is a well-defined convergence in complex numbers. So everybody knows it, but I say that this converges to this. So now this is the evaluation maps, because let me say if I know, I didn't write it down. So if I want to write this in a more physicist things, I can.
Really, you better write this part of the book because it will be visible to everyone.
Okay. So this delta xn of A is a state. Okay? Now probably I should write bigger. Delta xn of A is a state. Okay? Now A at the end of the day becomes a function of the space. So I am allowed to write this as A of xn, no? Because this xn is a point. Okay, so this is called the evaluation map. It's something which takes an element of the algebra and gives you a number. But this is what you do when you evaluate a function in a point. Okay, so a point is an evaluation map. No? So it's I have the set of functions and I have a point, which means that any functions will have a value at this point. Functions are continuous.